to this presentation of this morning. Dr. Crow is our presenter this morning. The man is a seasoned structural geologist that have some idea of CV because I was chairman of the awards committee when he was given the Akin George Award in Nigeria. So he has worked extensively on the geology of certain parts of Africa. Now he's working in Nigeria. He obtained a PhD degree in structural geology from the University of Adelaide in Australia. I hope I'm correct. And he has worked extensively. He taught in the university, and he has worked as principal, the principal partner for his company. And he has tremendous experience in mineral exploration all over Africa. And so he's working on gold and nickel, chromium, platinum group element mineralization in the western part of Nigeria. We will listen to him, how far he has done, what accomplishments they have been able to achieve. So, Dr. Crow, you are welcome, sir.
Okay, thank you, Prof. Welcome, colleagues, and thank you for the invitation to present our work to date on the NIMAP program. So we've been working on the Lot A1 part of the program, and this is I guess everyone would probably understand at this point that this is a federal government-sponsored project undertaken in collaboration with the NGSA. And as I said, we're working on the Lot A1 program, which includes 2 projects. So we're looking at the gold vein type mineralization, and we're also looking at nickel, chrome, cobalt, PGE, magmatic style mineralization. So our area that we were, I guess, assigned to undertake this work was Western Nigeria. So it's an area that covers 300,500 kilometers. And to develop this program, we had to build an understanding. So for our initial targeting, we had to develop an understanding of the structural development in Western Nigeria and apply what we understood about the gold controls to this model to develop some of our early targets. So with the result of that first phase of work, we identified 9 project areas through the area where we were going to initiate ground programs. And so these are through the states of Zamfara, Kebbi, Niger, and Osun. The stages of work that we were undertaking can be broadly defined into 3 areas. So the stage 1 was actually defining the project areas where we were going to initiate our groundwork. So as I mentioned, that was involving a regional structural interpretation, given that gold mineralization that we're targeting is all structurally controlled, and integrating with that our understanding of the controls on the gold mineralization through Nigeria and the relative timing and how that fit in with the structural evolution of Western Nigeria. So once we had identified those target areas, we initiated some ground programs that started with initially regional field mapping to identify, I guess, zones within that broad area. And then we undertook ground magnetic data acquisition and geochemical sampling programs. So the initial geochemistry was done on a regional basis, and then we infilled to define target zones. So on the basis of the targets that were defined, we moved to what we call a stage 3 mineral deposit definition, where we would follow up with the drilling. So we're towards the end of the stage 3 program now, and that's primarily what I'll be talking to you today about. So these are the primary data sets that we use for the stage 1 approach to build up our structural model. So it was the national airborne magnetic and radiometric data sets. And our starting regional structural model was the basis that we developed our targeting models on. So just on the right-hand side, we can see some of the phase one structural models that we came up over a number of areas to delineate potential target areas. So these are one of the ones from up in Zamfara and one in Kebi. So the project areas, we've defined 9 project areas. So you can see them labelled through there. So we've got sort of 2 of those were primarily associated with the PGE nickel chrome targeting, and we've also defined another one in Tsauni as well. So we've got three of those project areas, and the rest were gold targets. So of these project areas, we've defined 5 areas that we undertook our stage 3 work programs. So we initiated drilling programs in 5 areas. So there was Talata, which is a PGE nickel chrome target, and then Talata South, which was a gold project, and 3 projects in Tsauni, so 2 gold and 1 nickel chrome PGE target. So just covering some of the statistics in terms of work completed in the project. So we've undertaken over 21,000 test pits. So these pits are what we use for our soil sampling. So we ran a pilot study to determine what was the most optimal type of sample and depth of sample to take. So all our samples were targeted to be collected at the base of or at the top of the saprolite zone, at the base of the weathered zone, and the pits were dug to reach that zone. So we're comparing apples with apples. So for instance, you know, some pits might only be a ½ metre, other pits might go down to 4 or 5 metres. We've submitted about 23,500 samples to the lab for analysis. We've collected nearly 30,000 XRF data, and we've covered about 22,000 kilometres of field mapping. In the ground magnetics, we've collected 8,500 line kilometres of ground magnetic data, 46 line kilometres of EM data, 2,400 kilometres finished the work. So I'll start on Tsauni and look at our 3 project areas that we've got there. The Tsauni area, our prime target was this shear zone. It's quite a distinct target area. It's very different to most of the other gold mineralisation that you see further west in Nigeria. It's not associated with schist. It's hosted in felsic gneisses. It's on a late stage structure that's not part of the main late structural features that cross Nigeria, and it's on the margins of what we're calling the Eastern Structural Domain, which is quite a distinct structural entity to the other domains to the west. And I guess in part, as an aside, what may be a driving factor of this is when we look at the satellite gravity. You can see sitting right under this zone in here is a very large gravity high, which we think was an important control in controlling the geometry, the structural geometry that formed in here. So here we've got what we think are low angle structures overprinting more north-south basement structures. The other interesting fact is this feature may well have also exerted some control on the Cretaceous deformation. So we see the Bitter Basin forming in the back of that, behind that intrusive complex. And also of interest is the extensive, I guess, dikes that are probably Jurassic to early Cretaceous in age that cross-cut western Nigerian field area. They don't occur over this body. They're to the north and to the south surrounding it. So this is something that we don't fully understand, but there appears to be, I guess, a coincidence of features that are related to it. So back to Tsauni. So this was our target area. This is the airborne magnetic. So you can see that this structural zone is characterized by a demagnetization that's truncating the main structural fabrics in the surrounding host. We collected, that's our area of interest. So it's quite a big area. It's about 12 kilometres by 7 kilometres. We collected ground mag over all of that, and you can see, even in the ground mag, you can see how the magnetic response is quite disrupted by this demagnetization. This is the interpretation of the structure. So we've got a mafic gneiss sequence through here, and basically different grades of felsic gneisses, and we've got these late brittle ductile fault shear systems running through here, and potentially a late intrusion placed into this zone. Here we have attempted to try and map out the relative degrees of, I guess, demagnetization through the area, just to see if that had any correlation with the distribution of mineralization. We ran some soil programs to define some of these targets. So the initial soil program in the phase 1 was a 50 metre by 500 metre line space soil, so quite regional. And on the basis of those results, we infilled down to 125 metre by 25 metre soil sampling to delineate our target zone. So you can see the gold zones became quite prominent through this area, while the arsenic was stronger in this block. The gold values were quite scattered and irregular, so nothing coherent through there. Strong lead association through this zone, a little bit less. What was interesting, we also had very strong nickel, chrome, cobalt association through here, through this zone. And this, when we look at gridding this geochemical data in that zone, you can see we can actually map out distinctive structures or features that are associated with the different commodities. So on the basis of that geochemistry, that soil geochemistry, we defined 3 target areas. So this one here we call Tsaurni East. Now this is this little magnetic unit through here. And this is what's associated with the nickel, chrome and cobalt anomalies that we define. So this is an ultramafic suite of rocks that runs through this zone in here. These 2 are gold project areas that were targeting some of the strong soil anomalies through this area. So we currently have more or less finished work in our Tsauni West area. We're probably not going to do much more on Tsauni East, and we're just in the middle of the drilling program in Tsauni South. So these are where we've been drilling and our collar positions. So this is the ultramafic unit in Tsauni East. So it's not a single unit. This comprises about 5 to 6 individual ultramafic packages that are coming up, possibly dike suites intruding into the felsic gneiss. In the Tsauni West, we were targeting 4 veins, and one of the criteria that we used to select the gold areas was where we had multiple vein systems in close proximity, with the rationale that if you wanted to develop a mine, then you want to try and get width, particularly if you want to go into open cast. You want to have grade across width and not just along a single narrow vein. And similarly, our Tsauni South was where we started targeting what were a close set of veins that were overlapping. So you can see we've done quite a bit of drilling in Tsauni West, a reasonable amount in Tsauni East, but we paused that, and I'll talk a bit more about these two projects in a bit more detail. And Tsauni West is more of a recon drilling program, just to try and define the sorts of grades that we have in each of the veins and the broad extent of them. So this is the drilling in Tsauni East. So we've got relatively low grade intersections of nickel. So we're looking at 0.2 to 0.4% nickel, and relatively low grade palladium platinum numbers of 0.08 to 0.06 grams per tonne. So they're a bit on the low level, but what was interesting is that they were defining, I guess, horizons that were more enriched than others. So the eastern ultramafic units appear to be more important. And you can see the same in the palladium and platinum results. Now, on the basis of this, we step back. And thinking, right, this mineralisation seems to be patchy and zonal. So we thought we'd try and target some new areas that may provide better numbers, stronger grade numbers. So to that extent, we undertook some really detailed infill soils in a number of target areas. So one just to the north of the drilling. So this is a drilling here that we've undertaken. So just about 100 metres north. We undertook another one, and that's on a 10 by 25 metre grid. And we did another couple of areas to the south. So you can see we've actually got quite some strong results in through this zone here. So we plan on putting a hole into this just to see what sort of grade numbers we'll get out of this. We're hoping there'll be a big improvement on what we're getting in through here. Tsauni West. So we were a bit hampered with the wet season on this program in that we were unable to complete the drilling program as planned, particularly in these low-lying areas, which became very, very boggy. Even up in here, we were using a bulldozer to move the rig and the trucks around at the end. So it was very difficult conditions to drill in. But we did manage to complete most of the project. We've got, I guess, we've defined a very strong zone of mineralisation on one of the target structures. The ones through here, we got, I guess, relatively low grades, and we did pick up some stronger numbers on one hole to the west, which were only shallow. We did try to test the depth extent of that, and it didn't intersect anything. And that could be telling us something about what's happening with this vein system. So we're still trying to understand what's happening with this vein system. But with further drilling, we may be able to test out to the west a bit more. So just looking at some of the significant intersections we've got over the Tsauni area. So we've got some very good gold and silver intersections, and in particular we've got some quite strong width of intersections. So, you know, for instance, we've got 13 metres at 0.9, 12 metres at 1.2, 16 metres at 0.8, 8 metres at 1.1 grams per tonne, 15 metres at 0.7. So there's some very strong numbers defining this vein system through here. And importantly, it's open to the north, to the south, and to depth. So we certainly would like to extend the drilling in both directions and even to depth on this. All right, I'll just talk a bit about the Talata South project. Now, this target area came on the back of the work we're doing on the Talata Intrusive complex. So this is an ultramafic gabbro granite composite intrusive complex that we're looking for the PGE chrome nickel mineralisation. But while we're working there, we noticed in the metasedimentary units at the back of it, we had some volcanic units, and there were also a couple of artisanal mining sites through there. So the original brown mag extent that we collected over the Talata intrusive complex, we extended to the southwest to start looking for some gold targets. So this was a structural model that came on the back of that, where we've got dilational structures opening up in the back of the Talata intrusive complex. And from the mag, this was the lithostructural interpretation we've got. So you can see this is the Talata intrusive complex at depth, at the surface. It's represented by discrete hypotheses of these ultramafic units that is surrounded by these granitic bodies through here. And we've got politic units and volcanic units as a cupola to the main intrusive complex. Then we've got the main structures focusing at the back of this intrusive body. And these are what we thought would be interesting targets in terms of being dilation and having a good rheological contrast between our volcanic units and our metasediments through the area. So we ran some soils over the program. So we got very patchy gold numbers out of there, but we've got a few strong hits in through here, which need to be followed up. We also got coincidence arsenic anomalies through there, and then through here, and certainly up in here, and copper, coincident copper anomalies through some of these zones. So we're at this point, we've only done reconnaissance drilling, so we were attesting the extent of the mineralisation and the depth extent. So these results, we've, I think have probably been in the lab for a few weeks now, so we've got another few weeks to wait before we get any results. So yeah. So I'll talk now about this tectonic intrusive complexes that are associated with these ultramafic units that we're targeting. So we initially defined two bodies. So we've got the Talata intrusive complex and the Kumbo intrusive complex to the south. And we've also delineated another series of potential targets through this zone as well. But we only, while we did work on both of these in terms of up to stage 2, we only have advanced to stage 3 drilling on this complex through here. What's interesting about these bodies is that they're intimately associated with the Ankar shear zone. So they're a SnTectonic intrusive complex that's been in place up the shear zone. So different structural controls on these two. But what we did notice what we have seen in the Talata complex is that we've got a deeper, so you can see this is the outline of the deeper magnetic feature of the complex, and that's the outline here. But at the surface, all we see is this little ultramafic layered sequence of rocks. That's like an apotheose that's been emplaced through the metasediments, and then we've got a mantling, an outer, I guess, zonation of granite sticking out at the surface. So the ultramafic rocks we see on the ground, we get nice layered bands of chromite. Some of the chromite layers have been disrupted and broken up. And the implications of this is that it's not just a simple layered intrusive complex. This complex has been disrupted, and it may well have been disrupted while the thing was being intruded. So we're potentially looking at features indicating, I guess, a disruption during the evolution and layering of this complex, or intrusion of this complex. So we ran some soils over this, so we've got very strong nickel, chrome and cobalt, defining a core zone to the complex. And then we had an outer zonation defined by copper, platinum, and palladium anomalies. So on this basis, we were, well, they're quite broad anomalies. So, you know, the difficulty with this was where do you drill in this? So we ran an EM survey over the whole complex. Now, it was a moving loop around EM, and the main aims were, one, to look for direct targeting of massive sulfides if there are any present. And the other aim, or primary aim, was to try and map the geometry of this intrusive complex. So this is just some of the conductivity depth slices from the data. So even with these, we can actually see an evolution of what these units are doing going down depth. So from the surface or near surface, we can see this sort of circular structure with a nice resistive zone in the core. And as we go to depth, we can see this particular zone stepping out to the east, suggesting we've got a more conductive layer dipping east, and in here we've got a layer that is also dipping east, but a lot more shallowly, and flattens out, and ultimately we pass through it. And then we come into this conductive blob in here. Now this is the most conductive feature in all the data. And it's a nice, discrete little conductive unit at depth. And we think this is this body here. So we think this may represent an intrusive feeder pipe into the system. So you can see the flattening of this conductive unit out through here, and this is the dipping, east dipping conductive package in the east. Now this was an interesting feature, which its importance has, I guess, become increasingly evident with the subsequent drilling that we've done, in that we think this may be some sort of alteration system that we're yet to fully define. Now what's interesting at the surface in this complex is that the core of the complex has this silicification, and it's silicified peroxenites and things, and that sits right above this body. So it's all through here. So this is all a silicified zone sitting above this body. A voxel model we built on this data. So what we're looking at here is the most conductive parts of that voxel model. Oh, sorry, and this is a slice through the voxel model. Sorry, I should have mentioned that earlier. So when we take out all the, and just highlight the most conductive units of that voxel model, we can actually start seeing some of the geometry of the complex. So again, we've got this feeder pipe, and we've got these layered sequences through the body. So what we've tried to do is we've tried to interpret that and interpret, I guess, the structure and the significance of the various conductive units. So this is what we've ended up coming up with. So we've got our intrusive body sitting in here. This surface is a surface at the base of that conductor unit. So you can see it's quite disrupted. And that sort of goes to when we were looking at some of the disrupted chromite layers we see in the magmatic rocks at the surface. We can see this is not a simple layered ultramafic intrusive system. There's a lot more complexity to this. And when we look at some of the deeper areas, we're interpreting a basement or a basal section of granite, gabbro, intrusive units coming up underneath it. And we think a lot of the structures that we see, these faults, so here we've got some sort of graben feature that this feeder pipe's coming up. We think these are structures that are forming in the cupola above an upward advancing larger system. So we're layering the ultramafic layered sequence through an apothecary above it, and that's being pushed and up-domed from beneath by these gabbroic units and disrupting this layered sequence that we see currently at the surface. So in terms of the drilling, so we had multiple goals in this drilling. Because I guess first and foremost, we needed to understand where the mineralisation was within the sequence and what was providing the anomalous soil numbers, and where might we target that. So we had to determine, I guess, where in a layered sequence might our target mineralisation be. We delineated a number of BM plates that we wanted to test. So we've targeted 4 holes into those. And we also wanted to test that deeper feeder body. What is that? Am I still on? Hello?
Hello, you
Hello.
went off a little bit.
You are back.
We're back. Okay. So we've got some interesting chrome numbers. So we've got, at this that we've got in so far, we've got chrome numbers between 0.8 and greater than 1%. So the greater than 1% is where the analysis method has reached over limit. So that currently those over limit values are getting reassayed to give us a true value. So all we know at this point is the value of sort of, I guess, supports what the artisanal miners have known for years. And I guess ultimately we want to build a greater understanding of the gold and nickel, chrome, cobalt, PGE mineral systems in Nigeria, which can then directly feed into exploration approaches to develop more of these deposits. All right, thank you.
Thank you, sir. Thank you, sir, Dr. Crow, for the lecture. We will now take questions. So please, if you have any question, I've indicated that people should type in the chat section. People should type their questions. If you have any, please type it, or you can also ask directly. Are you hearing me?
Me? Oh.
Yeah. I've not seen any question typed. So I will assume that people want to ask directly their question. So if you have a question, please just indicate and ask your question.
There's one question there, sir.
Okay. Okay. I would like some comment on the style of the primary mineralization, please. He was talking of the style of the primary mineralization. That's his question.
For the gold or the PGEs or both?
Okay, you didn't specify, but maybe you take them one by one. For the gold first, then for the platinum group elements.
Okay. Well, I think the style of gold mineralization in a broad sense is all orogenic gold that we're looking at. We're looking at, I guess, relatively low temperature, high level mineralization. It's all consistent with sort of, I guess, emplacement sort of at 300, 400 degrees. What's notable, I guess, is the mineralization seems to be at a higher level in the north of Nigeria than the south of Nigeria, in that their structures that are hosting the vein systems in the north are more brittle, whereas down south they're a little bit more in the ductile or brittle ductile range. And I guess the other thing you notice is that there's more alteration associated with the vein systems in the mineralisation to the south than we see in the north. I guess perhaps quite significantly in terms of the projects we've worked on is we may be looking at models that have different sources. So a large percentage of the Nigerian gold mineralisation is hosted in schist belt material. And it's consistent with the, I guess, the metamorphic model for orogenic gold, where gold is sourced from the volcanosedimentary basin and then funded up some of these late major structures. And I think that's been demonstrated by some work done by Dr. Garber in Binyari that looked at some isotopic and geochemistry to support that model of a metamorphic model. However, when we look at Tsauni, we've got gold mineralisation hosted in gneisses, basement gneisses, potentially older basement gneisses. There's no immediate source. I guess the other thing is with this gold and another deposits around Nigeria is that we get a strong tungsten association. So while we don't see any evidence of late intrusive complexes through there to help explain that potential magmatic origin for the gold, we potentially may be looking at deeper sources. Now, the source of the gold could be from the subcontinental lithospheric model. We're right towards where a potential suture zone is between the west and eastern Nigeria. So again, I think there's a lot of scope for looking at having multiple gold systems in Nigeria. I think it's all in the same relative timing. So I think what's has been an important trigger for this mineralisation is a major change in the tectonism during the, moving from I guess a textural transgressional deformation that was accompanying the high-grade metamorphism right to, I guess, the later stages of exhumation that then switched to a synstral sense of movement. And that's probably got something to do with the docking of Antarctica, Australia, inclusion in the southern part of the Congo and driving that up. But that change in structural regime was, I think, a potential trigger for the main mineralisation of gold through the area. And once you've got these structures in place, you know, whatever sources of gold you're looking at are utilising that same structural trigger for the mineralisation. Now, in terms of the ultramafic and PGE mineralisation, I guess what's been notable is, I guess, the absence of sulfide in these things. Now, that could tell us that we've extracted sulfide into a sulfur melt and got some massive sulfide sitting somewhere that would be a nice target, but we haven't seen any evidence of that. So to me, these are looking more like more oxidizing systems and potentially similar to, I guess, a Bushveld type scenario, although not even on the same scale. The timing of these intrusive complexes are associated with the development or the localization of strain along these main structural belts. So, you know, moving from the closure of these intracontinental basins and inversion of these basins, where we started localizing the strain along those, I guess, zones of weakness. That is where we're moving up these ultramafic sequences along these structural zones. These are the conduits for bringing them to high levels in the crust. I guess significant, you know, key to that is that during that early extension phase, where we've attenuated the crust, we've probably had, I guess, upwelling of the asthenosphere into higher levels as beneath a thin crust, that once we close it up, we're just creating a conduit to move material up. I think the system that we're looking at in Tsaurni in terms of the ultramafic sequence is a bit different to what we're seeing in the anchor shear zone. These ultramafic units may well be telling us that we do have sources from the subcontinental lithosphere. I mean, we're bringing mantle material up right next to where we're getting gold mineralisation moving through these systems. So it may be just a window into what the source rocks are for the gold at depth.
So I also have a question here from Professor Akonde. He said, can we distinguish between the primary nickel and chromium mineralization, the primary and secondary type mineralization in those areas? Is there any way from your studies that you can actually differentiate between the primary and the secondary type mineralization for chromium and nickel in those areas?
I guess we're hoping to have some insight into that with our diamond holes. The diamond drilling is expected to start in the next couple of weeks. At the moment, most of our drilling has been done with RC, which I guess the benefit of RC with a big hammer footprint gives us a better sample for geochemical purposes, but it's very limiting in terms of seeing the relationship of the mineralisation to the host units. So once we get these diamond holes drilled, then we'll have core to look at. That'll give us a lot more information on that. Now, what we can say in terms of that from the surface is that we've got both. We've got some primary layered chromite that we can see in the ultramafic sequences, but we've also got chromite associated with discrete late cross-cutting vein systems. And yeah, at this point, we don't really have a full handle on that and what it means. But hopefully with these two diamond holes that we're going to put down, that'll give us a lot more information. And they're going to be big holes. They're sort of 250 metre holes, so we should get a lot of information from that core.
Okay, thank you. So I have this long comment from Professor Shinyama. So let me read it, and at the end of it, there is a question. The Tsauni occurrence is somewhat of a departure from what we know about relation of mineralization zone to the main shear zone. In Elisha, Anchor, the gold mineralization occurs associated with secondary structures at angle of 30 to 60 degrees from the main shear zone. In Tsauni, this is not the case. Are we now looking at a separate model for which we should look for similar areas?
Yes, I think that's entirely correct. I'll just show you a slide. Is this still up? Yeah. So is this still up on the screen? Am I still sharing?
Yeah, we are seeing it.
Yeah. Yeah, so this is a sort of a tectonic model that we tried to put together to help us think about what the controls were. So, you know, from our early extension, when we inverted it and we started closing up these basins, we've got our metamorphic gold mineralisation using these I guess high strain or these late shear zones where all the strain is resolving, and then we're replacing some of the ultramafics tapping from here. But this is what we think might be the Tsauni model, where our source is from the subcontinental lithosphere, where once, and I guess stepping back, you know, a driving mechanism for a lot of this extension may well be a slab rollback model, where as a slab rolls back, we're allowing hot asthenospheric material to underplate the crust. We're attenuating the lithosphere, we're forming our basins. And when we close that back up, we've got this I guess, metasomatized, altered subcontinental lithosphere material that is then tapped by these structures that bring up material. And that may be the gold source for Tsauni, which is quite distinct from the metamorphic gold source. And yet they're all happening at the same time, but in just different tectonic situations or scenarios across the block. Does that sort of answer the question?
Okay.
I mean, there's so much work that needs to be done to really pull apart this. You know, we're just pulling together observations and trying to look at other models that have been put out there around the world to see how that might explain our observations in Nigeria. But there's certainly going to be a lot of analytical work that's going to need to be done to really pull these systems apart.
Okay, thank you. Any other question? Do we have any other question? I can't see any other question.
There are questions in the Q&A column. Q&A column.
Okay, let me see. Q&A. Where is that? Okay, please read it. Read them so that I can see.
From Madam Lami Salah, what was the source of the realization based on the geochemical data obtained, please? The source of realization based on the geochemical data. He is asking what is the source of realization based on the geochemical data obtained.
Well, I guess in terms of the gold mineralisation, we've got, geochemically, we've got quite, I guess, two distinct types of systems. We've got, I guess, tungsten-bearing systems and systems that don't have tungsten. Now, these tungsten-bearing systems are typically associated with magmatic gold sources. And what you normally or would expect to find with those is a plutonic source that has gold, I guess, grade moving away from them and proximal to the magmatic source. Now, we don't see that in the deposits in Nigeria that have this tungsten association. What we see are these, again, they just look like a normal orogenic structurally controlled mineral system. So what we're probably looking at is potentially a deeper magmatic source. Again, differentiating from a metamorphic source, we may have the influence of fluids and potentially mid-level intrusive systems sourcing from the lower crust and driving, I guess, gold-bearing fluids that are sourced from the subcontinental lithosphere into higher levels. But again, you know, more specific work, you know, looking at you know, fluid inclusions, etc., and isotopic work would be needed to really pull this apart in more detail.
Another question from Professor Akode. What is the significance of silicification or alterations in the Tsauni area? The significance of silicification or alteration in the Tsauni area. What's the significance?
Yeah, again, we don't see an awful lot of silicification, but where we do see it, it's all associated with our vein systems that we've got in there. So, you know, I guess the sort of alteration that we're looking at is that we've got fluids taking advantage of some of these structures. And now these vein systems aren't just a straight single quartz vein. Show you another slide, what happened with our drilling. So at Tsaurni, where we drilled one hole, so our approach to targeting the drill holes is that we had a trench and we looked at the quartz veins in the trenches. So all the quartz veins in the trenches were dipping to the west, steeply to the west. So we planned our drilling to the east. So when we drilled, we've got intersections down one, but the hole coming underneath it, that's nothing. So it tells us that this vein does not go straight down. So this is how we've understood the vein systems that we're looking at in Tsaurni. They're in an echelon vein system. So instead of the veins dipping steeply to the west and continuing, it's a series of east dipping and echelon veins defining the structural zone. So, you know, that's when we started switching our drilling to the west to target these zones. So, you know, you see silicification in the wall rocks sort of along that zone.
Okay. There's another question from Professor La. The layered gabbro you mentioned with clear chromite layers, are they discrete massives, pods, or linked to the ophiolite series?
Yeah, I guess traditionally these have been called ophiolites, but we don't think they are. We think this is a layered intrusive complex that is syntectonic. So it's come up the actual anchor shear zone and been placed within the structure, within the shear zone itself. The layered chromite we see is a layered sequence. So it's not bodiform chromite, it's a nice layered sequence. We also see chromite in veins. We do see floating irregular rafts of chromite within pyroxenite layers, which we think are disrupted, broken up chromite layers that have been disrupted. The layering has been disrupted and incorporated into another melt layer. So that sort of goes to, I guess, the dynamic, structurally dynamic environment that this sequence was being deposited into. So it's, you know, in terms of being an ophiolite and the implications of that, we don't think it is, particularly these ultramafic units are related to it. And what you also see in these ultramafic units are hypotheses of gabbro, very coarse-grained gabbro, intruding into the layered pyroxenite layers. And that sort of goes to, you know, are we seeing these hypotheses of the deeper source bodies that we think are coming up and are disrupting that sequence?
Okay, sir. There's another question. Can we compare the Tsauni mineralization with those of the Duluth gabbro in the US?
To be honest, I'm not familiar with the Duluth gabbro, but there's no evidence. I think there isn't, while we do have a mafic gneiss to the side, and I think that's behaved as a strain focusing body, you know, in terms of the rheological contrast between the mafic unit and the felsic gneisses. So it's important in terms of where some of the deformation is focused and maybe where the ultramafic units have come up around that margins of that body. There's no evidence of late gabbroic emplacement through the area, not that we've seen in any of the drilling or the mapping that we've done. But again, I think what we're seeing is it's all part of the same orogenic gold system that we've got through the western area. And as I said before, we're just thinking we might be looking at different source mechanisms, but utilising the same structural system that's been applied, you know, on a regional basis.
Okay, sir. Another question. Did you in any way identify any relationship between the gold, copper, lead, silver, and the PGE mineralization, or are they completely isolated systems?
Yeah, well, we're looking at copper, particularly in Tsaurni, in the ultramafics, and we've got, I guess, very low. So, you know, I guess that was one of our interests in there, was that where we're looking at a nickel copper type target there, but the nickel is I guess at best sort of low grade so far, and the copper was no real numbers in the copper at all, even though we did have moderate copper anomalies in the soil, the actual grades coming out of those ultramafic units aren't very strong at all. So, you know, like I said, we want to put another hole in an area that we think might produce stronger numbers. So it'll be interesting to see what copper we get out of that area as well. In terms of the relation to the gold mineralisation, I think it is related in the sense that it's the same potential structural system that's providing the conduits for the ultramafic sequences to get to structural high levels, and where we're sourcing this gold mineralisation from. So what was interesting is, as part of our drilling for the ultramafic units in Tsauni East, was that we do have some vein systems that have low-level gold in it associated with those, just on the margins of those, but they weren't yielding very consistent or strong numbers at all. So, you know, I think there is a relationship, certainly in terms of the structural controls and potential source areas for both of these.
Okay. Another question. What are the challenges of existing artisanal mining on the structural mapping of the target areas?
Yeah, Tsauni is a very interesting case study in that, like I said, when we first went to Tsauni, there was about six artisanal sites, and it's just when we were running our soil program, more and more started appearing, and now we planned a drilling program. We sent the rig to site and found there was a big hole in the ground where we wanted to collar our hole. So we had to redesign our whole drilling program, because it's amazing how many artisanal miners are moving into there. So it is difficult, but again, the flip side of that is, in terms of exploration, artisanal miners provide invaluable information. You know, when you go to a site and there's 100 artisanal workings that go less than a metre, well, you know, they haven't found much. They might have found enough to interest them, but they're not making any money out of it. It tells you that the mineral system there is probably quite weak. You go to another site where you've got 60-metre shafts, you know they're mining good and getting good gold out of that. So when you step back and look at all of those locations where you've got well-developed artisanal sites that are producing gold, you can start looking at the patterns. So they're like mini drill holes. They give you that sort of information, and you can start understanding the broader mineral system and then target on the back of that. So that's sort of what we had been doing through this program. You know, part of our when we're out mapping is that we collect information on all the artisanal sites, not just the location of an area, but we get a GPS point on every shaft and measure with a tape measure the depth of the shaft. And that builds up into a story that feeds into understanding the mineral system in an area.
Okay, I think there's a question on what is the general depth of drilling?
Sorry?
The depth of drilling.
Depending on where we are. So in Tsauni, we've drilled, at the moment, we've drilled down to 200 metres. We've got some deeper holes planned down to 250 metres. But typically, like in a gold situation with our vertical or steeply dipping mineralised system, we'd have holes ranging from 50 metres, stepping back to 80 metres, stepping back to 100 metres. So, you know, just to test the depth extent of the mineralisation. For the Talata situation, if we're targeting the layering, then depending on the depth of the layering, we'll be targeting holes just to go through those layered sequences. So it's variable, but I guess it depends on the method you're drilling and the target you're after. But again, you know, in the early stages of exploration, you really want to define resources near the surface. you know, you don't want to be mining waste. So you want to be defining resources that you can actually mine near the surface. So yeah, I would suggest, for the most part, unless you've got something big at depth, then you probably don't want to be drilling any more than 350 meters.
Okay, sir.
Okay.
Over to you.
Thank you. Are you through?
Yes, sir.
Okay. Okay. Thank you. So we want to express our gratitude again to Dr. Crow for agreeing to give this presentation, and also to the Nigerian Geological Survey Agency for arranging this presentation. Before I hand over to the president, I just want to announce that what we have listened to now is just the first in the series of our seminars. The next one will come very soon, and it will be on the artisanal and small-scale mining in Nigeria, the current status, challenges, and prospects. It will be a roundtable discussion, and the panelists will be Dr. Garba, the DG NGSA, Engineer Nkom, the DG Mining Cadastre, and the Registrar of COMEC, Professor Bakunsho. So the time for that will be announced later, but I just want to tell us that we have another one scheduled already. It will come up very soon. So I want to hand over to Dr. Garba, now the president. Hello, Mr. President, sir. Are you hearing me? Hello? Hello? Hello?
Maybe the NMDS president should give his talk before Dr. Garba comes over.
Okay, the NMDS, okay. Is it there? The NMDS president, is it there?
Yes.
Is there?
Yes.
Okay, so my president, sir, please your comments, sir. Your talk. Engineer Nkom.
Are you talking to me?
Yes. I said your comments before we close. Please,
Okay.
your comment.
Congratulations for this webinar. And I want to appreciate the presenter, Dr. Warwick Crow, and the president of Economic Geology, Garba, and all the other panelists and stakeholders for this wonderful work. It's quite decisive and timely. I may want to make a comment so that when the president is making his comments, he's able to now say something about it, particularly when it relates to the Nigerian Mining Cadastre Office, whereby we work closely with climate project, demarcating and demarcating these areas and allowing the project to go on so that licenses not be granted over those delimited areas when the project is concluded. I know that it's coming in phases. There are members of the committee. I think for clarity, most of the operators are beginning to get restiveness on them to actually believe that for how long are these areas going to be demarcated and protected, and for how long again are they going to be deprived from getting, because when they submit applications, they will not be able to now get approvals. So I believe that it is in basis, and then the prospectivity areas will be brought out at a different stage. So I want the president, and particularly Director General of the Nigerian Geological Survey, to be able to now say a word to interested operators. I know that at the end of this climate project, areas will now be concessions for bidding investors, whether they are local or international. So on that note, I want to thank you for
Thank you. Mr. President.
Wonderful day. Thank you.
Thank you, sir. Yes. So we hand over now to Dr. Garba, the president of the Nigerian Society for Economic Geology. Mr. President, sir, are you there? Are you there? Are you there? Hello? Hello? So, hello? Hello?
President, we can see you, but we cannot hear you.
Okay, you are seeing the president.
Yes, we are seeing it, but we cannot hear him. And he's unmuted.
He's unmuted. So what's the problem?
I don't know. I think it's a technical issue.
Yeah, it's a technical problem. So, I've just spoken to the president now. Hello? Dr. Latunji?
Go ahead, sir. Go ahead, sir.
Okay. So now, so he has some technical challenges, and so he cannot talk. So he's saying that he's saying that I should just relay his message that currently they are looking at all those deposits from the economic point of view, but from the other academic point of view, they will still look at that. But the critical thing that has happened now, we are beginning to understand the mineralization system. And from there, we'll be able to develop methodologies in future to do proper exploration in other places. So now we're having a clearer picture now of our mineralization and how to look for them. That is the takeaway, generally. You said he would have liked to address some of the questions, but because he's having technical challenge and he does not even know what is wrong with the computer. So that's the issue. So he's also grateful to the presenter, and he's saying that the work continues. We are just at the first stage. The work continues, and we hope that we'll have an outstanding success concerning this project. So he wants to thank everyone that has participated, including the NMGS president, and everyone that actually logged, including Professor Molomo, Shian Molomo, who logged in, I think, from UK or something. So thank you all for coming, and God bless you. I will see you again, maybe January or something, for another seminar. Thank you for coming.
Thank you, sir.
Okay, bye.
And bye.